Now let's consider the mechanisms that are used by TCP for congestion control. Congestion control is one of the most difficult problems for TCP, and the reason is TCP cannot detect overload situation in the network. You remember, TCP is only running on the both end systems. The intermediate systems, they do not use TCP, so TCP has no chance to measure something to directly see the situation in the network, what happens on the path from the sender to receiver to adjust the speed of transmission. The data packets in the network are transported via Internet protocol. They can be transported over different passes through the Internet. So no direct conclusion can be drawn about overload on specific intermediate systems. Also, different TCP instances cannot interact. Only the two TCP instances that are connected by a virtual connection can cooperate. Other TCP instances on other pairs of communication partners, they cannot interact with each other. So in the idea that it's used, and it's quite successful, used for congestion control with TCP is the following. TCP interprets the number of loss, of packet loss. The TCP packages are called segments. The TCP interprets the number of lost segments as a measure for overload and as a parameter for determining the congestion window. Congestion window, that's the speed of sending data over the internet. This is quite clever because, of course, if a data package does not receive at the side of the receiver in the time set by the timer, then package is lost or package is delayed. Both show that there is some situation in the network which is hindering an efficient communication. So in this way, measuring the number of lost packets, and if the number of lost packets is increased, then it is quite fair, and it works fine in practice, to interpret this as that there is a load situation on the way from the sender to the receiver, which shows an overload situation and draws a conclusion that the speed, the transmission speed, needs to be decreased. The mechanism that's used by TCP to adapt the congestion window to the right situation in the network is the so-called slow start algorithm. The idea of the slow start algorithm is to find as fast as possible the right communication speed, the communication speed that adapts to the situation in the network to find the right congestion window. So connection start, if a connection is established, connection starts with a small window with only a few data transmitted, and then it's observed how fast the acknowledgement is receiving. And then in the next time, twice as much, exponentially raising number of data are sent up to the moment acknowledgement does not receive. So in this way, the speed is fastly adapting to what's possible, what's the right congestion window in the network. To reduce congestion situation, there is the congestion avoidance algorithm. The congestion avoidance algorithm works as follows. If segment losses accumulates, that means if acknowledgement do not reach the sender within the set period of time, TCP lowers the sending data rate so as to try not to increase the network situation, not to increase an overload situation by continuously repetition of transmission. So if segment loss is found out, then the transmission speed is lowered, not to increase overload situation. This is this idea of the congestion avoidance algorithm. There is one more mechanism. This mechanism is the Nagel algorithm. Nagel is the engineer who introduces. This limits the overhead when transmitting data packages. If TCP package has just a short length, so only a small amount of information is sent, then compared to the load, the overhead information is in a bad ratio. We have the TCP header. You remember the TCP package, the header together with the load is the load of an IP package with an IP header. So if there is only a small amount of information to send via a TCP connection, then the efficiency, the ratio between overhead information and load information decreases. So that the majority of the transmitted data are administrational data. To avoid this, the Nagel algorithm proposed to do the following. First, the acknowledgement, which is a relatively short message. The acknowledgement of a segment is delayed as long as possible. So to collect more information that need to be sent from the receiver to the sender. The idea is to enrich the payload. The payload, for example, by also sending one times several acknowledgements, same time in same package. So collecting information, taking several types of information within one TCP message to increase the efficiency of the transmission. Then the transmission of the own payload is delayed as long as possible in order to send it together with outstanding acknowledgements. So if there is a bidirectional communication, then on each side they have to send back to acknowledge on one side the receive of a data packet. On the other side, they want to send new information. This can be done within one package. So the Nagel algorithm is a mechanism of TCP that collects all payload until the next due acknowledgement and then transfers both together. Of course, this needs to be very fine-tuned, because if it's wait too long with sending back the acknowledgement, then sender considers a package as lost. So this should be avoided, because this initiates a retransmission, and also this is not good for the efficiency of the network. So the central question in the adaptive retransmission was to determine the round-trip time, RTT. This was, you remember, the time between sending out a message and receiving the acknowledgement. And this was the measure that need to be done to adjust the timer in the right way. To avoid congestion, one needs to avoid retransmission as much as possible. But if the timer is not set to the right way, the efficiency cannot be guaranteed, because then the sender waits too long before starting new transmission. The question is how this round-trip time is determined. And this is determined with every transmitted segment. And then there is a weighted calculation to compute, for example, a mean with the round-trip time from the transmission in the past. And exactly the question how this weighted average is calculated. This can be done in different ways, and first proposal or first implementation was done by Partridge, and the Partridge algorithm entails this idea. The problem in the very original organization of this round-trip measurement and this average computation was that there could be failures for the following reason. A package is sent out and no acknowledgement received in time because package was delayed. So package is retransmitted, but the package arrived late in the receiver, and the receiver sees this error is free and then backs the acknowledgement, because the receiver does not see when the package was sent. So this late acknowledgement is taken into the computation that this was the first transmission, this was a retransmission, and the acknowledgement comes here. So in the computation, in the original computation of the round trip time, this short time was taken into the calculation of the mean. And of course, this was a wrong value. The right value would be this one. And if this occurs several times, then the weight, the average, is not well computed. So Partridge repaired this situation in the way that in their algorithm, only this between the sending a message and the right acknowledgement is taken into the computation for the round trip time. So the calculation is based only on the measurements of segments that were actually acknowledged by the receiver. In addition, the time limit is raised after each successful delivery, although this is a little bit from the experience and the observation of the everyday experience. The internet, in particular the complex TCP protocol, that's a huge technical system, and there is many experience and to find the right values. You remember, if round trip time is measured too short, it leads to a timer with small limit, too small limit, and if it's too long, then the efficiency of the transmission is not okay. So there is a lot of thinking about determining the round trip time in the best way. Next proposal comes from Carroll and Jacobson. They refined the Partridge algorithm by weighting the fluctuation in the measurement of the network round trip time. So if it's increasing, then there is a forecast of increasing. It's increasing and decreasing. So there are different reactions on the situation. And in addition, the Carroll and Jacobson algorithm performs the calculation of the timeout in an adjusted way.